Hello and welcome to College Physics 1, Lecture 21, Solving Circular Dynamics Problems. In our previous lecture, we introduced circular motion, that is, motion of an object in a circular path, but at a constant speed. That said, we also found, though, that even though it's moving at a constant speed, the object is accelerating because it is constantly changing its direction. And remember, velocity is a direction and a speed together. So anyway, the point is that our object is always accelerating, and as a result, it is always experiencing a force. That is, a force holding the object into a circular path. If that force wasn't there, the object would just go flying off in a straight line. So our goal today is to learn how to solve problems dealing with the forces in circular motion, and then just practice a few examples and a few questions at the end. So let's first go through a problem-solving strategy on how to solve a circular dynamics problem. The good news is that these problems work the same as all of our other force problems, in that you draw a free body diagram, write out Newton's laws, and then solve. The bad news, if there is any, is that drawing your free body diagram has a little bit of an added complication now. But we do it on purpose. We complicate our free body diagram setup just a tiny bit so that our math actually becomes easier down the road. So, here's something weird. Up until this point, we have always drawn the same x and y axes, right? And up until this point, I don't know, I'll put this over here. We've always drawn our axes like this and said, this is x, this is y. But we're just choosing it to be that way. We're going to change it up now. From here on out, what we're going to do is always draw the x-axis so that it points toward the center of the circle. Regardless of what problem you have, keep this in mind. It's very important. The x-axis always points toward the center of the circle. So technically, that means x could be any of the sides of our axes. So you'll see that in an example very soon. Just keep that in mind. So you'll have one of two situations when you start one of these problems. If you have a problem where the motion is in a horizontal plane, such as, I don't know, a ball rolling around in a circle on the ground, or a car traveling around a circular track, then what you do is draw the free body diagram with the circle viewed edge on. Meaning it's like an ant's eye view. Like imagine you're an ant on the ground looking at that circular path. You're looking at it from the edge. Again, your x-axis must point toward the center of the circle, which means that your y-axis will be perpendicular to the plane of that circle. I mean, that just makes sense. Our x and y axes are always perpendicular to one another. Now, if the motion is in a vertical plane, such as, a plane doing a circle through the air, or a roller coaster going through a loop-de-loop, we would draw our free body diagram with the circle viewed face on. In other words, you looking straight at the circle. So you could be standing looking straight into the circle of a loop-de-loop on a roller coaster. But again, the x-axis will always point toward the center of the circle. And as a result, that means in this case that the y-axis will point tangent to the circle. We'll see examples of each of these soon. Once you've drawn your free body diagram, you write out Newton's laws. In this case, you will write out Newton's laws, your sum of forces in the x and the sum of forces in the y directions. But here's the good news. Because of the way that we drew our free body diagrams, assuming we of course did it correctly, our x equation for every circular dynamics problem will equal mv squared over r. And again, note that this is coming from F equals ma, right? So you have F equals ma, but in circular motion, A is v squared over r. And so that's where this equation is coming from. So we used to set our equations equal to ma, but now we're being specific and saying it's mv squared over r. So we're setting it up so that the x-axis is the one that always has the force, because the force always points toward the center of the circle, and we're always drawing our x-axis toward the center of the circle. So that's where our force is. So that's where we write our equation, mv squared over r. So every problem you do should have x set equal to mv squared over r. And thankfully, because of this, we will not see a sum of forces in the y direction. There may be forces there, but the sum of them is 0. They balance out, in other words. This is true for every problem. Now, in our previous problems that we've been doing, we had to always find an acceleration. It didn't matter if we were using forces to find a position or a velocity, or if we were using positions and velocities to find a force. Either way, we had the crossroads of needing the acceleration. Here, it's very similar, but instead of an a in the equation, we have a v now. So for these problems, you always have to find the speed if you want to find anything else. So you're either going to use your net force equations that you just wrote to determine the speed, and then use circular kinematics to find things like frequency and period, or you can do it backwards. Use circular kinematics to determine the speed from a period or frequency, and then use that speed in the equation above to solve for your forces that are missing. So I recommend referencing this problem-solving strategy anytime you work out one of these problems. It may help you if you're a little bit confused on where to go next. Well, we've looked at our problem-solving strategy. This entire lecture is called Solving These Problems. So let's go ahead and do 2 examples and a few questions. Example number 1. A father places his 20-kilogram child on a 5-kilogram cart to which a 2-meter rope is attached. He spins the child around with a tension in the rope of 100 newtons. How long does it take to complete 1 rotation? And note, we're going to ignore friction. All right, well, let's just start real quick. It's asking for how long does it take to complete 1 rotation. So this is technically asking for the tension, the period. How long does it take? I already made that confusing statement. So remember in our last lecture, we learned that unfortunately period is represented with capital T, but so is tension. And this is a problem that has tension and period involved. So we're going to have 2 different capital T's, which, why make things easy, right? So that's not my rules. I'm just following them. So let's just set up real quick a visual of this. So I'm really bad at drawing circles, especially on a drawing pad. But you know what? That's not too bad. Here is our circular path. And so let's just say we have our father in the center. And the kid is over here on the cart. So this has some radius r. And let's just say we're moving in this direction, which would make this a counterclockwise direction. So let's say this is our setup for the problem. Well, our first goal is to draw a free body diagram. So let's start there. As always, draw your axes and represent your object as a dot at the center. Well, we have to first figure out which direction the x-axis would be pointing. Well, in the setup that we have, the kid is over here, which means the center of the circle is to the right. Right? So the kid's here, the center of the circle is to the right. So to the right is where we label our x-axis. We've set it up so that our axes look normal for the first example. So let's think about what forces are acting, assuming again friction is ignored. Well, every object on Earth has a weight associated with it, W. It's on a surface, and so it should be experiencing a normal force straight off of that surface. My arrow's a little crooked, but it should be straight up. And we have a force holding the kid in toward the center of the circle. This is the tension in the rope. Again, this should be straight to the right. These are the 3 forces acting on the child. Well, the child in the cart. So we want to first, now that we've written our free body diagram down, we want to write out Newton's laws. That is, the sum of forces in each direction. So in the x direction, there's only one force, and that's the force of tension, T. As we've said in our problem-solving strategy, this is where the acceleration is, so we always set this equal to mv squared over r. In the y direction, we have two forces, the normal force N minus the weight W. And this is always, in circular motion, in the y direction, equal to 0. Okay. Well, following our problem-solving strategy, we're looking for the period. That's circular kinematics. So, what that means is we're supposed to use our equations that we've written to solve for the speed first, then solve for the period. So let's do this. Let's solve for the speed. We need to rearrange the equation, so let's multiply both sides by r, then divide the m underneath, and then take the square root to get rid of the square. This will give us v is equal to the square root of tr over m. Okay. Well, we do know the tension, it's given to us. We do know the radius, and we do know the mass, which means we can solve this problem, for the speed, at least. We have the square root of the tension, which was 100 newtons, times the radius, which was 2 meters. And this is all divided by the mass. Be careful. It's a kid in a cart. They both have a mass, which means we have to take into account the total mass, which is the 20 kilograms of the child plus the 5 kilograms of the kid. I'll write it out in full, so I'll say 20 plus 5. Just to be clear. I could just write 25, but it might be more clear if I write this as 20 plus 5. Plugging this in, you will get approximately 2.83 meters per second. Okay, well, we now have our speed, which means we can finally use circular kinematics to solve for the period. We have an equation from our notes. I'm going to kind of separate this a little bit. We have an equation in our notes that says speed v is equal to distance over time. The distance around a circle is 2 pi r, and the time it takes is the period. This is not tension. I know it's very confusing, but this is tension over here is a force. This is period. We want to solve for the period. To do that, you basically just swap the places of v and t. And so we'll find that the period is equal to 2 pi r over the speed. We have the values to solve this, so let's do it. 2 pi times the radius of 2 meters, all divided by the speed that we just found of 2.83 meters per second. This gives us an answer for the period of about 4.4 seconds. So this is how long it takes the kid to complete one revolution around his circular path. Okay, so this is really the only equation we have for period. So even if you didn't look at the problem-solving strategy, you'd probably find this equation and then realize, oh, I need the speed v here in order to solve. And so you would have to go back and find it first. The problem-solving strategy is really just a way to kind of guide you toward the answer to help you, figure out what steps to take if you're unsure. Well, let's solve another example. Since this is new to us, let's do one more for now. This problem, example 2, says a level curve in a road has a radius of 150 meters. What is the maximum speed at which the curve may be traversed on a rainy day when mu s equals 0.4 between the tires and the road? This time, let me set up the problem so that we have, like, here is kind of our circular path. This is only part of the circle. This is the right-hand side of it. And let's say here's our car, right on the edge. And so we're traveling, let's say we're traveling this way, in a counterclockwise direction. Well, we know that there is a radius associated with this. This goes all the way out, so this is a large circle. So here we are, over here. Let's draw first our free body diagram for such a problem. I'm going to kind of tuck this down here in the bottom. We know that we have our two axes and the dot in the center, and we have to think again, be careful about the direction of the x-axis. The x-axis always points toward the center of the circle. The way I've drawn it now, for this problem, the center of the circle is to the left. So our x-axis is pointing to the left. So this is weird. We normally label it over here, but now the positive x-axis is to the left. Okay, so again, your x-axis always points toward the center of the circle. In this case, it's to the left. So let's think about the forces that we have. This is a horizontal motion problem, so we're going to look at the circle edge on. So we have our standard weight pulling down on the vehicle. And it's on a surface, so a normal force pushing back. But be careful. There is a force here acting to hold the car in place. In other words, to stop it from sliding off the road. So it's weird to think about this, but in the context of this problem, the force that's holding the car in toward the center of the circle is static friction. And it's in toward the center of the circle. It's holding it in. This confuses people. A lot of people put kinetic here because the car is moving. But we're talking about the force relative to the center of the circle. The car wants to fly out off of the circular path, so static friction's holding that in. It's stopping the tires from skidding sideways off the road. Yes, the car is moving forward, but we're talking about the tires not skidding away from the road. So just be careful. These are the three forces that we have. Now, this allows us to set up Newton's second law. The sum of forces in each direction. This problem will take a little bit more work than the last one, as you'll see very soon. To set these up, we have one force in the x direction, and it's to the left, but that's the positive x direction, so this is actually a positive value here. Positive static friction. And, as we've said before, by rule, it's in the x direction, so this is set equal to mv squared over r. In the y direction, we have our fairly standard normal force minus weight equal to 0. Which, while we're at it, let's just say this means normal force equals the weight, which by definition, if you recall our equation for weight, is mg. Okay, so this is step 1 and 2. We're on to step 3, which basically just says solve the problem. Well, this one is a little bit more complicated. We do know that we have to find the speed. We're looking for the maximum speed, so we have to find this speed v, which only shows up right here in this equation. So let's start there. We want to solve for speed, and so let's rearrange our equation for that. To solve for speed, I'm going to multiply r next to f, divide by m, and take the square root. This gives us v is equal to the square root of fs times r over the mass, all in the square root. Okay, this is good. We're looking for speed, but we don't yet know the friction value, f, and we don't know the mass. So there's a complication here. Well, let's think about what the definition of friction is. Right? So let me write this off on the side. We know by definition that friction the equation is mu times n. Okay, well, we do know what mu is. It's given to us as 0.4, but we don't know what the normal force is. But thankfully, we kind of do. Because in the y equation, the normal force is equal to the weight, which is m times g. So this becomes mu s times the normal force, which is given as mg from the y equation down here. So now we can take this equation for friction and plug it in down here. So let's go ahead and do that. We have the square root of our friction force, which is, again, mu s times mg, times the radius r, divided by the mass. Now, in this case, notice what happens. We still don't know the mass m. But the good news is we have an m on top and an m underneath. Those m's cancel out. I believe I've said this in a past lecture, but if you're ever working on a problem where you swear you need to know the mass but it's not given to you, it's a likely indication that it's going to cancel out somewhere. And that's the case here. We needed the mass. We needed it to solve for v, but it wasn't given to us. So it's a hint that it should cancel out. So this leaves behind a much simpler equation. The m's cancel, leaving behind mu s g times r. We do know all three of these values, which means we are now able to solve this problem. Mu s was given as 0.4. And remember, this is unitless. It's just a coefficient. In other words, just a number. G is the 9.8 meters per second squared. That is the acceleration due to gravity. And r is the radius of the circular path, which is 150 meters. All of that's underneath our square root. So, if you plug this into your calculator, you should get approximately 24 meters per second. So what this means is this is the minimum speed that you can use to traverse the road. If you move any faster than this, then you're going to start to skid and slide off of the road, which is not ideal. So this is one of the reasons why you certainly have a maximum speed on a road, especially when it's raining and the roads are more slick. Okay, so this used a combination of several equations, right? I mean, we used our x equation here to set up the problem, but then we realized we needed the equation for friction, which plugged in the equation for normal force into there. And then we plugged all that back into the equation for speed. So this stuff can get tricky because you're combining multiple equations. So just be careful when practicing this. But that at least gives you two really good example problems to work with. For now, we're going to just look over a few questions to conclude this lecture. And then in our next lecture, we will look at apparent forces in circular motion and practice these some more. So with that, let's do a few questions. Question number 1, and all of these are going to deal with drawing free body diagrams. So let's just make sure we understand the forces that are acting on each of the objects that are going to be shown. So the first one says, a physics textbook swings back and forth as a pendulum. Which is the correct free body diagram when the book is at the bottom and moving to the right? All right. Well, this actually kind of just takes us back to old material. We have to think about what forces are actually acting here. We should know that there is a weight acting downward. All of these show a force pulling downward, so, I mean, that's good. There's also a tension in the rope. Right? We have a tension up in the rope. That's a really bad arrow, but that is an arrow, I promise. We have a weight pulling it down. I'm writing at kind of an angle, so it's hard to see this. And that's it. A lot of times students will still make the mistake of putting a force in this direction, but there isn't one. There's nothing pushing or pulling the object to the right. So be careful. Now, there are not three forces. That rules out D and E. We just have to now understand which of the two forces is larger. Is the weight bigger? Are they equal, like in B? Or is the tension bigger, like in C? Well, the answer is C. Your tension is the larger force. The reason is because that's the force pointing toward the center of the circle. And remember, we always have a net force in circular motion that points toward the center of the circle. So whatever force is the one pointing toward the center has to be the larger force by definition. So we will definitely see C being the correct answer. Tension's bigger than the weight because tension's pointing toward the center. Let's do another one. A car that's out of gas is coasting over the top of a hill at a steady 20 meters per second. Assume air resistance is negligible, and I'll also say assume friction is negligible, so no friction or air resistance. Which free body diagram describes the car at that instant? Okay. This is somewhat similar to the one we just looked at. We know that the vehicle is going to have, gosh, I can't draw arrows today, a weight pulling it down, and it's on a surface, so there should be a normal force pointing upward. We're ignoring friction and we're ignoring air resistance. Still, even though we just did the last problem, students still like to put a force forward. But again, that is not true. There's nothing physically propelling the car forward, especially in this case when it's just coasting along the ground. So all we have is the normal force up and the weight down. Again, this just brings us to understanding which of the forces are bigger. Is the weight bigger downward, or is the normal force bigger upward? Again, force or net force points toward the center of the circle. The center of the circle is down here, right? It's down below. So the larger force has to be whichever one is pointing toward the center. And in this case, that is the weight. So the answer is A. The larger force is your weight pointing toward the center of the circle. Okay, let's do one more, and I really like this one. This usually you get a couple like tilted heads from students in person when I bring this one up. A roller coaster car does a loop-de-loop based on the picture to the right. Which of the free body diagrams shows the correct forces acting on the car at the top of this loop? Okay, well hopefully at this point you're understanding that there's nothing propelling or forcing the car forward. There is not going to be a third force. Let's talk about what is acting on the person in the cart though. There is a weight associated with the object that points down. All of our options show a weight that points downward. But here's where it gets interesting, and we have not seen this before in any of our work yet. Think about the fact that this cart is on a surface. It's on the track. The surface is up here though. So here is your surface. Well, remember, normal force by definition always pushes back against the object, which means if the surface is above you, much like if I pushed up on a hard ceiling, the ceiling pushes back downward. Oddly enough, the normal force is also downward with the weight. The answer here is E. So this is kind of a weird one. We haven't seen this yet, but in our next lecture, we're going to take a closer look at this type of a situation and work out a few problems based on it. So with that, I think it's a good point to stop before we get into those apparent forces that we'll discuss. As always, thanks for watching and have a great day.